In today's data-driven world, machine learning models have permeated various sectors, from finance to healthcare. These models, often dubbed black boxes, excel at making predictions. However, understanding their internal workings can feel like navigating a labyrinth. This is where SHAP, or Shapley Additive Explanations, values come in, acting as our guiding light. Imagine SHAP values as a powerful lens that allows us to peer into the decision-making process of machine learning models. They provide a clear, interpretable measure of how each feature contributes to a model's prediction for a specific instance. Whether assessing credit risks in finance, predicting patient outcomes in healthcare, or detecting fraudulent transactions, SHAP values empower us to trust and understand these complex models. But what happens when the very tools we rely on for interpretation are influenced by the model's internal mechanisms? This is the intriguing puzzle we aim to unravel today, focusing on a specific scenario: SHAP Value Dilution in XGBoost models. XGBoost, short for extreme gradient boosting, reigns supreme in the world of machine learning, consistently topping competition leaderboards. Its success can be attributed to a clever combination of techniques, one of which is col_sample_by tree, a form of feature sampling. Think of feature sampling as a strategic selection process. Instead of using all available features to build each decision tree in the XGBoost ensemble, col_sample_by tree randomly picks a subset of features. This seemingly simple trick offers a triple advantage. It combats overfitting by preventing the model from memorizing noise in the data, accelerates training time by reducing the number of features considered at each step, and promotes diversity within the ensemble, leading to a more robust overall model. While feature sampling undeniably enhances XGBoost performance, it inadvertently introduces a twist in our story. As we'll soon discover, this seemingly innocuous technique has profound implications for SHAP values, particularly when dealing with highly correlated features. In an ideal world, each feature in our dataset would hold unique information, contributing independently to the model's predictions. However, reality often presents us with highly correlated features, variables that move in tandem, carrying overlapping information. When col_sample_by tree enters the picture, it disrupts this delicate balance. By randomly selecting features for each tree, there's a chance that some trees might be built using only one of the correlated features, while others might use a different one. This random selection process can lead to the SHAP value of a particular feature being diluted or spread across its correlated counterparts. Imagine two friends, A and B, equally capable of solving a problem. If only one is allowed to tackle the problem at a time based on a coin toss, we might mistakenly perceive the chosen friend as more capable. Similarly, SHAP values influenced by col_sample_by tree might misrepresent the true importance of correlated features, attributing more significance to the one randomly chosen more often. Let's step into the shoes of a financial analyst tasked with building a loan default prediction model. We have a data set containing various applicant attributes, including their income and credit score. Intuitively, we know these two features are often correlated. Individuals with higher incomes tend to have better credit scores. We turn to XGBoost, employing col_sample_by tree for its performance benefits. After training our model, we eagerly turn to SHAP values to understand the factors driving predictions. To our surprise, we find that income appears to have a disproportionately large impact on the model's output compared to credit score. Have we stumbled upon a groundbreaking insight? Not necessarily. This seemingly counterintuitive result could be a prime example of SHAP value dilution. Since income and credit score are correlated, their importance might be artificially skewed due to the random feature selection process during tree building. Section 5. Peering under the hood, how feature sampling skews SHAP values. To truly grasp the mechanism behind SHAP value dilution, we need to delve deeper into the heart of XGBoost. Each tree in the ensemble learns by partitioning the data based on different feature thresholds, ultimately arriving at a prediction. The SHAP value of a feature is then calculated based on how much it contributes to the model's final prediction across all these trees. When col_sample_by tree is at play, the story takes a turn. If a feature is frequently excluded during the random feature selection process, its contribution to the final prediction, and consequently its SHaP value, gets diminished. This effect becomes particularly pronounced when dealing with correlated features. Imagine a game of tug-of-war, where each player represents a feature, and their strength reflects their predictive power. Correlated features are like teammates pulling on the same side of the rope. When colsample_bytree randomly selects players, some teammates might get more chances to participate, creating an illusion of greater individual strength, while their combined effort remains the same. The implications of SHaP value dilution extend far beyond theoretical curiosity. In high-stakes domains where model interpretability is paramount, misinterpreting feature importance can have significant consequences. Consider a healthcare scenario where an ML model assists doctors in diagnosing diseases. If SHaP values, influenced by feature sampling, erroneously attribute greater importance to a particular symptom due to its correlation with other symptoms, it could lead to misdiagnoses and inappropriate treatments. Similarly, in finance, relying on diluted SHaP values for credit risk assessment could result in biased lending practices, unfairly denying loans to deserving individuals, or extending credit to high-risk applicants. The stakes are high, and understanding the nuances of SHaP values in the context of feature sampling is crucial for responsible AI deployment. While the phenomenon of SHaP value dilution might seem daunting, there are practical strategies to mitigate its impact and ensure accurate model interpretation. 1. Awareness is key. Acknowledge that feature sampling can influence SHaP values, especially with correlated features. Don't blindly trust SHaP values without considering the model's training process. 2. Explore feature interactions. Instead of focusing solely on individual SHaP values, investigate feature interactions. Tools like SHaP interaction values can provide insights into how features work together to influence predictions. 3. Adjust colsample_bytree. Experiment with different colsample_bytree values. While lower values promote diversity and reduce overfitting, they might exacerbate SHaP value dilution. Finding a balance is crucial. 4. Consider alternative sampling techniques. XGBoost offers other feature sampling methods like colsample_bylevel and colsample_bynode. Explore these options to see if they mitigate dilution while maintaining model performance. By adopting these strategies, we can navigate the complexities of SHaP value interpretation in the presence of feature sampling, ensuring that our pursuit of model interpretability remains grounded in accuracy and reliability. While SHaP values have gained immense popularity for interpreting complex models, it's essential to remember that they are not the only tools in our arsenal. The field of machine learning interpretability is constantly evolving, with researchers developing new and innovative methods to peer into the black box. One such alternative is LIME, which focuses on building locally faithful explanations for individual predictions. Unlike SHaP, which aims for global interpretability, LIME creates a simpler, interpretable model around the instance of interest, providing insights into the factors driving that specific prediction. Another approach gaining traction is counterfactual explanations. This method aims to answer the what-if questions, revealing how model predictions change when input features are altered. By understanding these counterfactuals, we can gain insights into the model's decision-making process and identify potential biases. The key takeaway is that there is no one-size-fits-all solution for model interpretability. The choice of the most appropriate tool depends on the specific application, the complexity of the model, and the type of insights we seek. As machine learning models continue to permeate our lives, the need for transparency and accuracy in their interpretations becomes increasingly critical. SHaP value dilution, as we've explored, highlights the importance of understanding the nuances of model behavior and the potential pitfalls of relying solely on simplified interpretations. By acknowledging these complexities, embracing a multifaceted approach to model interpretability, and fostering open discussions about the limitations and potential biases of these powerful tools, we can pave the way for responsible AI development and deployment. Ultimately, our goal is to build AI systems that are not only accurate, but also trustworthy, interpretable, and aligned with human values. By embracing the principles of responsible AI, We can harness the power of these technologies to create a more equitable and just future for all.